So welcome back to Discrete Optimization. This is Constraint Programming Part 3. And today what we're going to do is look at the rich modeling language of constraint programming. One of the key aspects of constraint programming is the fact that the language is able to capture very complex model, very complex side constraints, idiosyncratic constraints. And the purpose of this lecture is to give you a feel on how you express these models in constraint programming. So I'm going to start with a very simple example. You'll see very simple examples today, but every one of them is going to illustrate some aspect of the richness of the language. So this first example is called magic series, and a series, S0 from Sn is magic if element I of the series, Si, represent the number of occurrences of the value I inside S. Okay? So what you see here is the array from 0 to 4. That's a magic series of size 5. And what we have to do is find these numbers, okay, such that the series is magic. Okay? So can you find a magic series? Come on, guys. Find a magic series. Okay? So I'll let you think a little bit. Okay? So this is one magic series. Okay? So you see 2, 1, 2, 0, 0. Why? Well, 2 there for 0, so that means that there are 2 occurrences of 0. You see 1 over there, 1 over there. 1 occurrences of 1. This is itself, right? So this is a little bit self-referential. And then you have a 2 there, which basically tells you that there are 2 occurrences of 2, this one and that one. Okay? And of course, there are 0 occurrences of 3, 0 occurrences of 4. Okay? So now what we have to do is to write a program that will find magic series up to 1,000 or something like that. The length of the series would be 1,000. Okay? And you can do this. Okay, so this is a simple model, okay, for doing this. Okay, so what we have there is essentially the size of the series. Then you have a range, and then here you have the decision variables. Okay, so the decision variables, you have one decision variable for every element in the series, and it denotes the occurrences of that particular element inside a series. Okay, what you see over here are the constraints, and that's the most interesting part. Okay, for every value, okay, from 0 to the length of the series. Okay, so you have one of these constraints, and that constraint specifies the number of occurrences of k inside that series. Okay, and how do you do that? Well, you have this expression here, which is basically summing for all I inside a series. Okay, and what are we summing? We are summing this, these constraints essentially, this condition, which basically tests if element I of the series is equal to k. Okay, so one way to think about this, in a sense. So this is the key in this example. So one way to think about this is that assume that every one of the decisions variables have already been given a value. What you're doing here is testing if this condition is true or false. Okay? If it's true, it has the value 1. If it's false, it has the value 0. So what you are really doing here is summing all the constraints and finding out if they are true or false. And if they are true, you get a 1. If they are false, you are a 0. And that's essentially equivalent to summing the number of occurrences of k inside a series. Okay, so what you see here is what is called a reified constraint. It's a very, very useful concept, and it's basically the ability to transform a constraint into a 0, 1 value, okay, into a 0 and 1 variable. Okay, and so as I said before, the variable is going to get the value 1 if the constraint is true. It's going to get the value 0 otherwise. Okay, so let me explain a little bit how this whole thing works. Okay, so this is essentially taking the model and unfolding it. Okay, so that you see every part of the sum. Okay, so you see there series 0 is what? It's the sum of series 0 is equal to 0 plus series 1 is equal to 0 and so on and so forth. Okay, so you are testing, how many of these variables have the value 0. Okay, for series 1, it's exactly the same thing. But now you are testing if the series 1, if series 0 is equal to 1, if series 1 is equal to 1, if series 2 is equal to 1, and so on. Okay? And so you basically have this big system here of constraints. Every one of these sub-constraints here, every one of these constraints consists of many, many sub-constraints that you see over there. Okay? So now you have to find this series, of course, and one of the things that we can do is start giving value. Okay, so if you give the value 1 to series 0, what is happening? Well, essentially you put a 1 over here. Okay, so that's the value that you have. Okay, and now, of course, by definition, if series 0 is equal to 1, you know that there is at least one occurrences of 1, and that's what you see over there. Okay, so we took the test over there. It's true now. You have this 1 over there, and of course all the other values there, they are false, and therefore you replace them by 0. Okay, and so this is the new system now. Once you have this additional piece of information, you simplify the whole system of constraints. Every time a constraint becomes true, you replace it by 1. Every time a constraint becomes false, you replace it by 0. Okay, and so now, for instance, at this point, you know that series 1 is greater than 0, and therefore you can look at, that value. Now this is series 1 is equal to 0. You can remove it, and once again you simplify the overall system. That's what's going on behind the scene. That's how the propagation works on reified constraints. Okay. So what is happening behind the scene? This is what the system does when it has a system including reified constraints. Essentially what it does, it replaces every one of these expressions by a Boolean variables. Okay? So you have these Boolean variables that you see over there, and then you state constraints, and these constraints are basically ternary constraints instead of binary constraints now. Okay? So you have a constraint which is called bool EQ, okay, which now takes 3 variables, okay, the Boolean variable that we just introduced, and then Si and K, okay? And basically a constraint like this is the specification of the constraints, right? So bool bxv, okay, and that constraint is going to be true if b equal 1 and then x has to be equal to v, or if b equals 0 and then x has to be different from v. So essentially what we did was taking all these reified constraints, and we replaced them by these ternary constraints and the new Boolean variables that we introduced. Okay? And then when we do the sum, this is piece of cake, right? So the only thing that we are using here are basically the Boolean variables. Okay? So in a sense, the beautiful model that I've shown you is basically automatically compiled by the system into a system like this, into this model, which essentially doesn't reason about reified constraints anymore. It reasons about natural, simple constraints between Boolean variables and other variables. Okay? Now let me move to another example, which is called the stable marriage problem. Okay? So now here I'm not going to define what I'm not going to argue about what a marriage is. This is a scientific problem here. Okay? And for the purpose of these examples, which have been defined a long time ago, okay, the marriage is going to be between man and woman. Okay? And so what we are interested in doing is essentially marrying this couple of beautiful people. You can see how beautiful they are, right? And we have to marry them such that the marriage are going to be stable. Okay? So, once again, we have a bunch of men, and we have a bunch of women, okay? And we have to marry them together. The only inputs that we get is that for every woman is going to provide a ranking for the man. Okay, so that's what you see there, and of course every man is going to do the same for every woman. Okay, so you see there, Hugh is basically ranking Angelina on top, and then Holly, and then Kara, and then Julia. Okay, and then on the other directions, Holly likes Clive very much, and so on and so forth. Okay, so for every woman you're going to get a ranking of the man. For every man you're going to get a ranking for the woman. And now we have to make sure that these marriages are going to be stable. Okay, now, we have absolutely no clue how to make people fall in love. We even have less clue to make sure that they stay in love. But we're going to do a scientific approach to this problem, okay? And this is the key, okay? So these are called the stability rules for a marriage, okay? So, and we're going to say that a marriage between Hugh and Angelina is stable if 2 conditions are true. The first one, if Angelina prefers another man, let's say George, right? So just taking, completely randomly George, okay? So if Angelina prefers George over Hugh, then George must prefer his spouse over Angelina, okay? So Angelina wants to switch to George, but George says, no, I'm fine, And so, of course, you have to have the opposite rule, right? So if Hugh prefers another woman, let's say Julia, over Angelina, then Julia must prefer her spouse over Hugh. Okay? So in a sense, what you have is that, Hugh and Angelina may not be very happy. They both want to switch, but they can't. They are stuck together. Okay? So that's why the marriage is stable. Okay? So that's what we want to do. We want to write a model here such that we design a set of stable marriage for all these Hollywood stars. All right? So what are the decision variables? Well, there will be 2 sets of decision variables. There will be, for every man, we'll find a wife, and for every woman, we'll find a husband. Okay, so that's going to be the decision variable, and that's what you see at the bottom here, right? So for every man, you find a wife, which has to be of course, a woman in this particular case. And then for every woman, we have to find a husband, which is in this particular case a man. Okay? You have the data here. Okay? So you see all the men, all the women. You have also the preferences for the man and the woman. Okay? So W rank of Hugh, Julia means what is the ranking of Julia in the ordering of Hugh. And the lower the value, the higher the preference for the particular woman. Okay? And of course, vice versa for the man. Okay? So this is basically telling, what is the ranking of Hugh inside for Julia. Okay? So the first thing we have to do, and this is actually very, very nice, is we have first to specify the rules of marriage in this particular example. Okay? And the way we'll do that is simply by specifying that, if I'm married to someone, that someone has to be married with me. Okay? And this is what these two rules here are basically saying. Okay? For every man, the husband of the wife of that man has to be the man itself. Okay? And, equivalently for the woman. Okay? So the wife of the husband of a woman has to be the woman herself. Okay? So that's the first set of rules that we have to express. And there is something really, really interesting about these constraints, right? So what you see here is that, wife of M is a decision variable. That's a variable, and it's indexing husband, which is also an array of variables. So you have essentially a variable indexing an array of variables. Okay? Very expressive feature of, constraint programming languages. Okay? Now the next thing and the last thing we need to do is to actually state all the stability rules of the marriage. And that's what you see in the last 4 lines here. Okay? So we're going to take every man and every woman, and then every woman and every man, and we're going to state that the marriage has to be stable. Okay? So what you see here is the first stability rule. Okay? And what this means is that M prefers W over his wife. Okay, so that's the left part of this condition. Okay, left part of this condition, of this implication here, is the fact that M prefers W over his wife. Now, if this is the case, what we have to make sure of, okay, is that, the woman prefers her husband over M. Okay, and that's what the condition that you see here is expressing. Okay, so essentially what we have here is a condition which is saying that if a particular man prefers a particular woman over his spouse, then it must be the case that that woman prefers her husband over this man. Okay, and so once again, what is interesting here is 2 things. First, it's a logical implication. Okay, nice. We can express all kinds of logical constraints in this language. The other things that you see here, which is very interesting, and once again, what we have here is a 2-dimensional matrix of preferences. Okay, matrix, it's a matrix of int in this particular case, but we index it here, okay, as you can see, by a decision variable. Okay, so once again, a big array, a big matrix here, indexed by a decision variable. Okay, so that's all we need. That's the entire model, and with that, we can solve all Hollywood problems. Okay. So there are 2 interesting features, I told you. The first one is called the element constraints. It's the ability to index an array or a matrix with complex expression involving variables or single variables. And then we have the ability to actually implement logical combination of constraints. Okay? So that's just what I said to you. Okay? So let me go into a little bit of the details of these features because they are interesting, and what you want to understand is how actually they are used in pruning the search space. Okay? So we're going to look at the simplest element constraints, right? So we have x and y, which are variables, okay? And we have an array C, okay? That array C is an array of constant in this, okay? It could be an array of variables in the most complex case. In this particular case, we are just an array of int, okay? And then the constraints is this thing, okay? So we are basically saying that C is equal to cy. Okay, so once again, this C here that you see, okay, that's an array of int, okay, and y is a decision variable. Okay, x is a decision variable as well. Okay, now this is an example. Okay, so I'm gonna show you the various examples. You see x over there, and the value that it can take, the x over there, it can take the value between 3 and 5, and you see y there, which can take the value between 0 and 5. Okay. So that's the domain of these variables when we start. Okay, so I'm going to assume that we have them. Okay, then you see the array C. Okay, so this is the array. At index 0, it has the value 3. At index 1, the value 4, and so on and so forth. And at the last index 5, it has the value 3. Okay, so that's what you see over there. Okay, now what is this constraint doing? Okay, if I have the information that x has to be equal to x is not 3. What's going to happen? Of course, the first thing we can do is remove that value from the domain of the variable. Okay, that's what you see over there. Okay? But can you deduce something more? Okay? So what we know is that what the constraint is going to do is, look, you know, the constraint is x is equal to cy. So we want to prevent y from taking a value that's going to give 3 to x. Okay? How do we do that? Well, we look at the value inside the index, which has a 3. Okay? There is the first one, the index 0, and there is the last one, which is index 5. Okay? So we have to actually remove the value 0 and the value 5 from the domain of y. Okay? And that's what you see there. Okay? So we remove the value 0, we remove the value 5 from the domain of y. So in a sense, what is interesting here is that if I know some more information about x, I can propagate it directly on y. Okay? So now, assume that I've learned something about y. I learned, for instance, that y cannot be 4. Okay, what's going to happen? Well, y cannot be 4, so what does it mean? It means that y here, you know, I cannot index this array with that particular value. And that particular value is 4. Okay, so it basically means that I remove this. Okay, but nothing happens at this point. Okay, because the value 4 can also be obtained if, you know, y is taking the value 1, which is over there. Okay, so at this point, I can't remove any value from x. Okay, so this is essentially only removing some part of this array, but, you know, I can still assign the value 4 to x. But if y now is different from 1, then I can remove this value 1 over there. Okay, please, yes. And then essentially at that point, you can see that the only value which is left for x is the value 5. And therefore, x has to be equal to 5, which is what you saw, which you saw just before. Okay, so I'm running over the animation again to tell you that the end game here has only one value which is left for x, which is 5, and only two values which are left for y, which are 2 and 3. Okay, so that's the element constraints. Two things which are interesting. Propagation goes from y to x and from x to y.